Hello everyone, and welcome to today's webcast, Reverse Engineering Mac Malware. My name is Trevor, and I will be moderating this webcast. Today's featured speaker is Sarah Edwards, a SANS instructor. Before I turn things over to her, the Q&A portion will take place at the end of the webcast. Please feel free to submit your questions at any point by using the questions window. Right now, I'd like to turn things over to Sarah.
Thanks, Trevor. Hope everybody is having a good evening, at least. Well, I guess it's evening on the East Coast, depending on where you are. Hopefully you're still not at work. Anyway, I'd like to get started. So reverse engineering Mac malware. Now this presentation came about as a second part to a presentation I did prior, when Macs get hacked. So when Macs get hacked was basically going and finding what malware has done to a system, where to find the actual malware, and things associated with the actual compromise. So what happens when we actually get that malware? So this is how that presentation came about. So my name is Sarah Edwards. I am a government contractor with Parsons Corporation doing quite a bit of mobile research, forensics, and testing, and all sorts of cool mobile stuff. I have done quite a bit of Mac, Windows, Unix, mobile malware, memory, all sorts of forensics related stuff in the past, but right now I'm focusing on a lot of mobile stuff. So if you don't know me, I am a Mac fangirl. It becomes pretty apparent when anybody talks to me or knows any of the previous work that I have done. And I guess they've found that that works for SANS instructors and authors as well. I'm the author and instructor of one of the newer one of the newer SANS classes, Mac Forensic Analysis, and that's FOR 518. And if you're interested, some of the material you'll see is pretty similar, but not too much. This is more malware based. But if you're interested in Mac forensics, come join us in San Diego, Virginia Beach, some pretty good locations, Las Vegas, Singapore, and Prague in October. Really looking forward to a lot of these locations. So the scope and agenda for this evening. We're going to do a lot of malware triage type stuff. So we're not going to go full on static reversing assembly windows. It is not to that level. It's basically, hey, is this executable legitimate or does it do some bad stuff? So I'd say it's about 20% static analysis and 80% dynamic. No assembly required. So if you were hesitant about joining, and hopefully you did join, about that, this is a very basic beginner type of analysis. And I'm going to go over various tools and examples and things like that as well. So to start off with static analysis. So first off, we need to locate and actually extract the executables. So some of them are in these embedded file types that make it kind of hard to actually get to that single executable that you can either do some quick reverse engineering on it or give it to your reversers to do some analysis on as well. So we're going over different file types. The various tools. So you'll see a lot in this presentation. I give you a few options to do the same thing. And it's mostly command line based options and GUI based options. So I think we all work in different ways. Some people are not a fan of command line. Some people are more visual people. I give you a couple different options. So take these, play with them. A lot of them are free. A lot of them are actually built right into the Mac operating system. And have fun with it. So locating the malware. A couple of different Mac-specific places where we're going to look for malware. Application bundles, these are your .apps, PKG or package files, and Mach-O executable. You will find malware in other types of documents, archives, and things like that. But when it comes to analysis, that analysis has really been covered in many other places. A jar is a jar is a jar. A zip file is a zip file on Windows as it is on Mac. So we won't be covering a lot of that because it's going to be the same analysis across the board. So we're going to go more into the Mac-specific examples. So first off, the application bundle. So this is your Safari.app, if you will, or anything in your applications directory. These .apps can actually be run from anywhere on the file system. You're not necessarily just going to find them in the user's application directory. It might be on their desktop. It might be in their downloads. You know, they can be all across the hard drive. So the basic structure of these is the whole point that they're called a bundle is that they're actually a bundle of a bunch of different files, not just a single executable. So there's some required pieces to this, and I give you some examples in the right. Now these are legitimate examples. We have Safari.app and Dashboard.app, but I'll show you an example of a malicious application in the next slide. So a couple of the requirements for application bundles. It's got to have an info.p list, and this contains information about, you know, what versions does the application run on, bundle identifier information, owner information, creator information, things like that. The executable. Obviously, we need something to execute in an application bundle. So in most cases, in most legitimate cases anyway, they're going to be located in that Mac-OS directory. So I'll just point out a couple of these here. So this Mac-OS directory, in probably 99% of the legit cases, that's where your executable, your Mach-O executable is actually going to be located. And you also have some other directories. You have some code signing information, some resources. Resources might include things like application icons or associated pictures associated with the application. So there's a bunch of stuff all located in these .apps. Now to get to these, we can actually do a right-click or context click of the .app and do open as, or what's the actual term, the open bundle as, or something like that. You'll see the option in that right-click menu. So a not so legitimate example. There's a piece of malware that came out maybe a couple of years ago called Crisis. Now, looking at the screenshot on the right here, I'm showing it to you with my cursor. We have this JLC3V7WE.app. Now, right off the bat, that's got a funky name. I'm probably going to look at it a little bit closer than, say, Safari.app. It just looks kind of bad. Now, this particular one has a lot of different stuff right in the root of the application bundle. You know, this is not what a normal binary application looks like. So I'm definitely going to take a closer look at this. And as it turns out, if we do like a file command on a bunch of these files in here, we actually get various executables, and I've put them over here for you. I'm not going to even try to pronounce them because they are really just random characters. But just looking at these files, we have no idea if it's a configuration file, a database, or if it's an actual executable. We even get a kernel extension with Crisis. So anything with a .Logkext is another type of application bundle. So it's going to have a whole other set of embedded files associated with it. So the one that I wanted to point out is this info.p list. Now this contains the application configuration information, but it also shows us the specific executable file that's being launched when somebody double-clicks this application. In this case, it's the IZSROY-MP executable. So next up, we have package files. And these package files come down as legitimate software all the time. A couple of them have an example over here called Flash Player 11 Mac OS. Now it might look legitimate, and Flash Player probably does come down as a PKG file, but this is actually a fake Flash Player. Flash Player is picked on quite a bit when it comes to Mac malware. Flash is picked on quite a bit in any respect, actually. But it's a good way to social engineer a user to actually double-click this thing, saying, hey, you can't play this video without actually installing this software. So these PKG files are extensible archive files called XAR archives. And Flashback. Flashback was a really big piece of malware. It really made quite a bit of news traffic back in 2012. If you know of any piece of Mac malware out there, you probably have heard of Flashback. It was probably the biggest one of all time, probably. So about 600,000 systems were infected with that particular piece of malware. And they all got installed by this Flash Player package. So because it's an archive, we have to get in there and actually extract the executable that's being launched when this thing is double-clicked. So in the top screenshot, we're running the XAR command with a couple of different flags on that Flash Player 11 package. And this is mostly just to see, all right, what's actually in this package, what are its permissions, timestamps, associated directories, and files. So I see, excuse me, two different directories in here that look particularly interesting, the payload and the scripts. That's probably where my executable is actually hanging out. So I take another program called UNAR. If you've ever used the Unarchiver, it's a great Mac GUI program to basically unarchive just about anything you could throw at it. This is the command line version of it. So giving you a couple of different options on how to extract these. I think XAR can actually do it with the -X extract option, but I like unar quite a bit. So I give that a try. So I unarchive everything, and let's see what I got. So right off the bat, I have this BOM file. All right, this is a bill of materials. This is expected. It's basically a receipt of what was packaged up in this PKG file. We have this payload and scripts over here. Oh, great. Okay, now we have gzip compressed data. So we go from package to gzip. So I'm going to use unar again. It's very versatile. It'll pretty much unzip everything. And we unarchive the payload and scripts archives. So once we do that, going down to this third screenshot down here, we finally see, okay, once we unarchive those, now we have CPIO archives to deal with. So there's multiple layers of compression in archiving in these particular PKG files. So, you know, just keep digging down and using UNAR to actually get to these files. So we went from PKG to gzip to CPIO. All right, finally, what do we get down to? All right, our payload directory actually turns up empty. Okay, no pay dirt there. Our scripts directory, however, shows us a Mach-O binary with called post install. And this Mach-O binary is a universal binary. I'll get to that in the next slide, with two different architectures. So this is what we're actually going to want to, you know, throw into IDA, throw into Hopper, and actually do some static analysis on. So the Mach-O binary. This is the primary executable format on OS X. So it's, you know, the alpha of the Linux world or the portable executable of the Windows world. They can be fat binaries, also called universal binaries. And why is it called fat? Basically because you can fit more than one binary into a single file. So you could have executables that have a PowerPC and a 32-bit executable, or a 32-bit executable and a 64-bit executable, all bundled into one file. Now because of this, you might also have different file signatures. So if it's a straight-up fat binary, two plus different architectures, you're going to have the file signature Cafe Babe. So if you are maybe carving for different executables, Cafe Babe would probably be one of the more popular ones that would come back. But just be aware, there's other file signatures associated with Mach-O binaries. So we have a specific one for 32-bit or 64-bit or 32-bit, 64-bit little endian. So there's at least 5 different signatures that you might want to carve for. Now, this is a little bit different than in the portable executable world, where if you just see MZ, you're good. So keep that in mind. A couple of examples down here. I have that crisis app again. And this is just showing us this is a Mach-O 32-bit little endian executable. And this is the signature here. So CEFA, EDFE. So it's not the Cafe Baby. It's not a fat binary. So just be aware of this. This is a single architecture executable. So moving on to the fat binaries, those Cafe Babes. A couple of examples here. So in the middle of the screenshot, I have an example of another one of those crisis executables that actually contains 2 architectures, so a 64-bit and a 32-bit. Now, why might they want to do this? mostly because during that the transition from 32-bit to 64-bit hardware that happened a few years ago, you could actually execute this file on any platform. And this actually came about back in the days when Apple was going through their Intel from PowerPC transition. So the universal binary, as it was originally comprised of, was a PowerPC and an Intel 32-bit binary. So it didn't matter if they were running an old PowerPC system or if they had a brand new shiny Intel 32-bit system, they could still run their whatever application that they want to run. It's portable in that respect. They didn't have to buy just one executable for PowerPC and then buy another for the 32-bit. So because these are called fat binaries, there's a tool called lipo. Very cute. Good naming on somebody's part there. So what lipo does, amongst a various bunch of different uses, is that we can get the actual architecture details of these fat binaries. So in the screenshot we see it's two different architectures, PowerPC, noted by the PPC here, and an i386, which is a 32-bit binary. So in this binary, we have two different executables, one at offset 4096 and the other at offset 49152. So we can go in and actually use lipo to extract a single binary. So we're not doing multiple analysis or on two binaries, or we want to do maybe a differential analysis. Does the PowerPC version work slightly different than the 32-bit version? Things like that. So to extract these binaries, we use just a simple flag called -extract and throw it out to an output file. So I have an example here of the Mac control. And Mac control is it was a semi-popular remote access Trojan. But I only want to look at, say, the 32-bit version of that binary. So I use the extract. I specify the architecture, which is i386 for 32-bit, and then I pump it out to another file for later analysis. So those are the command line versions. Now comes the tool MachoView. So we can get a lot of the same information from MachoView. It's a free tool, last I checked. We can get a lot of the same information on here. So in this mock header, we get the same information. We get what type of architectures, various offsets, and things like that. So I highly recommend playing around with each different tool. Another tool that we can't forget is strings or search strings from Sleuthkit. So the problem with strings on Mac, the one that comes with Mac, is that it doesn't do Unicode strings. And what does Mac really like? Unicode strings. So I tend to use search strings from Sleuthkit more often than I use the built-in strings function on OS X. So one of my favorite commands is search strings -e-b, and that's going to give you big endian Unicode strings. So be aware that you might not be getting all the strings that are there because of the tool that you're actually using. So looking at the strings for this particular binary, we see things like backdoor path. Okay, that's interesting. Usually if an executable has the word backdoor in it, I'm already kind of getting a little queasy. We see things with kexts. Is leopard, is lion? Is it doing a check to determine what type of operating system it's on? It's loading kext, it's unloading kexts. So it's probably doing something with kernel extensions. This is just a quick triage saying basically, hey, do I need to take a look at this executable a little bit closer or not? And in this case, I absolutely would. So again, going back to MachoView, we can still get a lot of the same strings. So we see that backdoor path. We see those kernel extensions, is lion, is leopard, all sorts of really great stuff. Another native tool, and when I say native tool, this particular one, NM, is native when you install Xcode command line tools. So it's free. You just have to download Xcode, install command line tools, and you should be good to go. So what NM does is it'll display various variables and function names. So it's displaying the symbol table for this particular executable. So in the screenshot here, we see a couple of different possible variable names or function names. Things like agent crisis. So this is the crisis executable that I did this add symbol dump on. You know, apparently it might have a demo mode. OS major and minor. Let's see what else. Other good stuff like BSD process listing, get system serial number. You know, it looks like it has quite a bit of functionality, and we can go dive deep with some other tools to get more of that functionality out of it. Oops. And again, back in MachoView, a lot of the same stuff. In the symbol table arrow on the left here, we can click the symbols and see a lot of the same information that we saw using the command line NM tool. And as the last thing for static analysis that I got is Hopper. Not a lot of people know about Hopper, but if you're on a budget, it is absolutely worth knowing. If you are an IDA user and you don't have somebody purchasing it for you, I mean, I think IDA's maybe upwards of $1,500, $2,000, something like that. Hopper, last I checked, was about 90 or 100 bucks, and it really does a really great job. It runs in Mac native. There's a Linux version. There's a Windows version. But as far as budgetary things go, this is fantastic for what you get. You know, it's a really good bang for the buck there. So I highly recommend if you got an extra 90, 100 bucks, you want to play around with some Mac malware, you know, absolutely go purchase this. It is a cool program. So code signed binaries. We have a lot of code signed binaries these days because of Gatekeeper, and I'll go over Gatekeeper in a few more slides. But Gatekeeper basically says, hey, if this executable isn't code signed with a developer, an authentic developer ID, it can't run on the system. So we want to extract a lot of that information. Now this sample that we're showing here, Kumar in the Mac, or KITM, this one was the first one to actually get to be newsworthy to quote-unquote bypass Gatekeeper. So it used developer credentials from Rajinder Kumar, whether it was Kumar himself or they were stolen or otherwise compromised, I don't know. But a lot of the malware was signed with this particular developer ID authority. So we want to use the code sign -d on a particular application or a Mach-O binary to actually extract this code sign information. So maybe you can determine if one particular developer ID has been compromised, and now it has 30 different variants of a particular piece of malware all signed with the same developer ID. So moving on to dynamic analysis. Talking a little bit about virtualization, some tracing, and again going into the tools. So virtualization. I think in dynamic malware analysis, virtualization is pretty key. You want to be able to throw a binary in there, execute it, capture a lot of the stuff that happens with it, and then revert, maybe change something, and then do it again. This is something we end up doing over and over and over again. Fortunately, there is software out there to do it. So VMware Fusion and Parallels are the two most popular virtualization software for Mac platforms. And virtualization capability actually came out back in 10.7. And some people know this, but not a whole lot of people do. And technically it came out in 10.6 if you bought the server version. So feel free. I think Apple gives you 2 virtualized machines in the EULA. So go nuts, play around. There's plenty of malware out there to be had, so play around with it. A couple of things that might be issues when we're doing virtualization and actually executing these things, these files. XProtect and Gatekeeper. So XProtect is Apple's version of antivirus. So 2 main files for this particular capability. XProtect.meta.plist and XProtect.plist. The meta file contains things of when the signatures were last updated, blacklisted plugins, what is the minimum Java version it can actually run, things associated with that. The XProtect plist is actually a little bit more interesting because that contains the actual signatures that the XProtect process is looking for. So this does have its weaknesses, as does every antivirus product. Apple updates it only when Apple wants to. There's very few signatures on the blacklist. There's only Mac threats on there, so there's no Windows malware, there's no Linux malware, no Android malware on there, purely Mac only. And it does no heuristics. And I'll show you an example of this in the next slide. So patterns and stuff, it really focuses on a certain file name or a certain path name. If a executable changes that up in a different variant, XProtect is probably going to fail. And the big one is it only checks quarantined files. So quarantined files are basically files that get tagged with this COM Apple quarantine extended attribute, example of which is shown in the screenshot. So this one is an extended attribute for a file that was downloaded with various web browsers or email or chat clients. So only specific third-party and native applications does this file quarantining activity. So make sure that you know which do and which don't. Now this particular one, I can see by the contents of it, this was a Google Chrome. So this xmount-0-5 was downloaded with Google Chrome. It's actually downloaded with this date here. And this is just a hex version of an epoch time. You can convert that. But any file that gets executed that has this COM Apple quarantine extended attribute as designated by the @ sign and an ls listing, it's going to go through the XProtect processes. Now, what's easy is that it can be deleted. So make sure that you, I think this is on the next slide, make sure that you actually go ahead and do the xattr-d, which is going to delete that extended attribute. So looking at signatures, the XProtect.plist file contains all these signatures that it's looking for. And I have an example up here in this lower screenshot of OS X coin thief. Now this one basically stole Bitcoining credentials and uploaded them to a C2 server so the adversaries could download all your Bitcoin wallets or something like that. So in this, there's a bunch of different keys in here, a couple that I want to point out. This identity key here, this is basically a SHA-1 hash that it's actually looking for. So maybe you have a different variant, it might have a different hash. It's not going to be protected because it's looking for this specific hash only. You also have a couple of other ones here. Launch services. So launch services is basically saying, hey, look for anything that gets executed as a Microsoft Word document that matches this pattern here. So if we extract this pattern, we just double click on that, extract it out to a hex editor, we can see exactly what it's looking for. So it's looking for a Microsoft Word document that's being launched from the /temp launch-hs or /temp launch-hse directories and other information associated with that execution. So say you have a different variant that has, launch-evil. It's not going to catch that because it's not in that pattern. It doesn't use heuristics. So keep an eye out for that. So this is how we disable a lot of the XProtect information. Obviously, we don't care if XProtect protects us when we're doing malware analysis. That is definitely not the way we want to go. Most of us don't even install antivirus, but this one comes with. So we're just going to have to disable it. So you can go ahead and just delete the XProtect files or just remove the contents of them, or go ahead and remove the actual quarantine extended attribute using xattr-d. So Gatekeeper. Gatekeeper is going to be another issue for us when we're virtualizing a lot of this malware. This is the anti-malware feature. It's basically saying, hey, you can only execute files that were code signed with a certain developer ID. But there's 3 different settings here. So we have Mac App Store. You can only run stuff downloaded from Mac App Store. Mac App Store identified developers. And then we have Anywhere. And Anywhere is what we're going to select for doing our malware analysis. That's going to let us execute anything we want in the system. You know, we can compromise our systems. It's a VM. We don't care, whatever. Just go ahead, select Anywhere, and it's going to let it go through. So if you don't want to do that, and maybe you just want to do it on a case-by-case basis, you can also do a control-click on the application itself. But of course, this takes a couple of extra steps, and I always forget, what is that key again on the Mac keyboard? Because sometimes I'm on a Windows keyboard on a Mac. So it might just be better just to go ahead and select Anywhere, assuming you are in a VM and not on your host system. Just be aware of that. So application tracing. Application tracing can be very useful. A lot of the developers out there might already be familiar with this one. It does some very low-level logging. It's incredibly verbose. It gets everything and anything you can possibly think of. But fortunately, we can filter through it and get some really good information that can help us doing our triage reverse engineering. You know, things having to do with file systems. You know, what files did it place? What file path was it looking for? You know, what attributes was it trying to access, and things like that. So with a couple of the tools that we're going to go over, Dtrace, which has some built-in tools, FS Usage, which is also built-in, and then we have Xcode Instruments. So going over a little bit about Dtrace, there's a huge, great book out there, and I'm physically talking, it is physically very large, about 2.5 inches, that came out all about Dtrace. So Dtrace is the scripting language. It's very awk-like. That'll allow you to capture certain data. So if you want certain file system data, if you want certain network information, what new processes have been executed or spawned, things like that. It's very, very useful if you know how to create your own scripts. If you don't, that's not a problem. There's a lot of built-in scripts already built into OS X, and I'm going to show you a few of those in the next few minutes. So Xcode Instruments. So Xcode Instruments is really just an interface to a lot of the Dtrace capabilities. It is a GUI-based system. You get it installed when you download Xcode. It's in the developer tools. And they have a whole developer instruments users guide out there. So just to show you a screenshot of what it looks like. It's very GUI-based. It's actually quite nice once you start getting into a lot of the more verbose tracing applications out there. And you can see visually, you know, where did things happen in timeline, what files were accessed. You can actually filter and search and all sorts of really great stuff. So in malware analysis, we often want to capture file system level events. So what files were created, what processes touch certain files or file paths, things associated with a certain file name. Was a file name created called evil dot I don't know, Mach-O or something like that. These are the tools that we can use to gather that information. So a few examples here. So file by procxp, or files opened by the process. I sort of go through and show you a couple of the different columns. For our purposes, really the function name, which is open : entry, and the process and path name are really going to be useful to us. So in this screenshot, we see that there was the touch process was creating a file called test.txt. The finder process was somehow accessing the Cliff Stoll user directory, and so on and so forth. You know, it doesn't give us a whole lot of information. There's another one, opensnoop-a, -a for all the data. But this one does a whole lot more information with at least timestamps and user processes or user IDs and associated information. So there's two timestamps associated with this output. We have a relative timestamp, so basically a tick count on the system itself. We also have this str time, so string timestamp of the local system time. So we can kind of get a good variance of, this certain action happened, and then maybe 30 seconds later this action happened. So timestamps can be very useful to us when we're trying to get a timeline of how a certain executable installs and what does it do afterwards. The user ID. So in this one, everything is user 501. But if something comes up as, say, UID 0, that might be interesting to us as well. Is something doing a privilege escalation where all of a sudden it has root access? So good information to know. So files created by processor, create by proc.d. Again, we have the function name and the remaining information, which is going to be mostly useful to us. So these are files created by processes. So in the screenshot, we have Google Chrome. This is pretty much all legitimate traffic for these particular screenshots. We have Google Chrome accessing the user's default Chrome directory, doing some stuff with local storage. And we can actually see the website that I was accessing at the time, www.rdio.com. So I was rocking out to some music while I was creating these slides. We can also see some information in here, and you can't quite tell if you don't know what you're looking for, but you see man, table, TBL, cat, trough, less. That's me basically doing a man on something. So while it's just a man for, say, opensnoop or something like that, there's actually quite a few processes going on in the background that are getting executed. And we can see that using these tracing scripts. So another built-in tool, fs_usage. Now again, this is very verbose, but it does have some filters so we can filter down specific information and target exactly what we're looking for. This -w here. Now you can use it with or without the -w, but I will just warn you right now, if you don't use the -w, it's going to cut off file paths or file names. And I'll show you an example a little bit later on in one of my screenshots. But we can use the -f and specifically say, hey, I want everything having to do with -exec for spawn processes or network-based events, things like that. So an example of that. So path name, so information relating to these file system paths. Some calls of interest. So gets and sets, always going to be pretty useful. So it's getting an attribute list or it's setting an attribute list. Open is very useful, of course, because it makes open files or creating new files. Make dir and remove dir. Is it removing directories? Is it making directories that could be of interest to you forensically? So a couple of examples here. Now I extracted these rather than giving you a screenshot, mostly because the output lines for this are absolutely huge, and a screenshot would just fail in these PowerPoint presentations. So the first one, the message on top, basically is saying the doc application, right here, the doc application is getting an attribute list of the messages application. So it's probably having to do with some sort of launch of the messages.app. Second example, we have Google Chrome. Now we saw Google Chrome accessing this local storage directory before. We can actually see that it's doing an open call on it specifically. So now we went over command line tools. Now we have GUI-based tools. So there's a tool out there, not native to Mac OS X, called fseventer, and it's available at fernlightning.com. It has a couple of different views that I'm going to show you. It also has filtering capabilities, and you can save all the output to a text file. So it's actually pretty easy and nice to use. So depending on the type of visual person you are, you might like this one. It's not my particular favorite. But it does help you kind of visualize where files have been deleted or changed, or click on them and you get some more information. This file was renamed 6.5 minutes ago, things like that. But the one that I really like is this tree function, and you can switch the views up here. It's very easy to do. You don't have to stick with one if you don't want to. But I like this one because it's easier to sort on. I like to do things by time. And I like to see, without having to click on it, what exactly happened. So this folder was changed, or this file was created. The extended attributes were modified here. And it gives you the processes and information associated with that. So this is definitely my preferred view. If I'm not doing it through a terminal using grep or awk and sed type stuff, I'm probably going to use this because visually it's very nice to look at. So that was file analysis. Now we're doing some process analysis, and of course process analysis is going to give us information about when we double click this application, what other processes in the background are being created or spawned, or what have you. So again, we're going back to Dtrace. Might as well use what's already on the system. Newproc.d, this is basically going to snoop new processes. So the information associated here, we have a timestamp. We also have process IDs and parent process IDs, so we can actually figure out, all right, this process is being spawned by this certain other process that is being spawned by this certain other process. These things can get very nested very quickly. We also get architecture information if it's useful to us. We also get command line argument application. So what was the actual process or application that was spawning all of these other processes? And down here, I can give you an example of open-a text wrangler. So that's me opening the text wrangler application from the terminal itself. And then on the next screen, it's a little fuzzy. But the next line, we have the actual text wrangler executable being launched. So we can see that correlation there. So new processes. We can use exec-snoop. I find this to be one of the most useful ones, and it's not too verbose. It gives you some timestamps, some user ID information. This is probably one of my favorites right off the bat. Just basically gives you what are the new processes, what are the spawn processes right off the bat. Very simple, easy to look at. Cat, I was doing XXD, text wrangler was executed, sudo was executed, probably I'm using the find command, text, gradi, trough, again that's using man something. So again, all those processes for the man command are actually running in the background. You think man was so simple, but it's really not. So back to FS usage. We can use it with the -f exec filter. A lot of the same information we can get here. So the two calls of interest, exec VE for new process and POSIX-spawn for a spawn process. So I extract these again because they get pretty long, as it were. And then this first one up here, so just take a look at this first line. We see launch-d, which basically everything on a Mac system gets launched by launch-d. Is actually launching the 0xED hex editor. So if you see something that's not being launched by launch-d, you definitely got to go take a look at it. Now these next four, again I'm using the man command, man on a certain utility, if you will. You see all this other stuff happening in the background. So we have bash is executing man, man spawns sh, sh is executing tbl, and then sh again is executing groff, groff. So a lot of the stuff in the background, but we can see it all with FS usage. So more of a almost command line, almost GUI based kind of thing. This is, I guess, the closest alternative we have on the Mac side to Process Explorer. So Jonathan Levin, author of the new OS X book, the Mac Internals book, which I also highly recommend if you are into Mac Internals and are looking for a newer book. He created a couple of really nice utilities. One of these is this procxp executable. Now it runs in the command line, but it does have a visual look to it. And this is real-time information. So we can see what processes are being run, what's the process ID, the prayer process IDs, the UID associated with it. If we click down and enter in the terminal on one of these processes, and this is shown in the blown out window to you, we get a little bit more information associated with it. You know, process hierarchy, what actually executed or spawned this particular process. We can't also forget Activity Monitor. You know, built right into Mac OS X. It's useful, it's pretty, it shows you the little icons, you can sort by things. It actually has quite a bit of capability. So definitely if it's the only tool you have available to you, please go ahead and use it. It actually has more capabilities than you probably think it does. If you do a right click on this header information here, there's quite a few more tables and columns that you can actually load into here to get quite a bit more information. So last up, we have network analysis. So these are things like, you know, what's going over the wire? What is it beaconing out to? What is it trying to download? So first application is a Mac-specific application. It's a Cocoa Packet Analyzer. You can download it from tastycocobytes.com. It is free. And it is what I can only say is like a Wireshark type interface. You know, anybody who uses Wireshark is going to be very familiar with this interface. You know, it captures packets, you can see the TCP and Ethernet and whatever information associated with it, as well as the hex view underneath here. Now, my one issue with this program, and I hope they fix it at some point because I'd really like to use it, is that it does packet caching. So it won't show you a lot of the information up here in this view here, because it waits until it has 10 packets, and then it puts it on the screen. And then it waits for another 10 packets, and then it puts it on the screen. So that's my only one gripe with that tool. But hey, if you're looking for a native application to look at, you know, network analysis, go for it. But there's the old good standby, Wireshark. Now this is an older screenshot. If you use the developer preview release that's available on Wireshark's website, it actually is native now to OS X. So no more X11. You don't have to deal with that. The interface is very Mac-like. It looks good. I've been using it for quite a while now, and I haven't had any issues with it. So I do recommend going out and downloading that developer preview edition, if you will. And if you're more of the command line type of folk, you probably are already familiar with TCP dump. If not, here's a couple of examples to get you started. So with or without content is basically what I was going for here. So TCP dump on top is basically just showing you the quick and dirty, you know, who is it coming from, where is it going to, what are the flags associated with it. You know, the with content might show you things like, hey, where is it beaconing out to, or what files is it looking for, and other information associated with that. So you know, your mileage may vary. You know, anybody who has TCP'd up experience might have like, oh, they're probably saying, oh, these are too simple. I can do so many other filters to get what I want. You know, absolutely go for it. TCP dump is a huge program with a ton of capabilities. We can't also forget Activity Monitor again. It does also have network capabilities associated with it. So in this screenshot, I sort of have it filtered by, you know, what application has sent the most bytes. You know, if an application is sending a lot of stuff out, and maybe I'm not supposed to know what it is, that might be a little bit more suspicious to me. In this case, it's just MDNS Responder, which is a perfectly legitimate service running on OS X. So no funny business going on there. And Jonathan Levin, again, created another tool. It's called LSOC. Now, this is going to be like the sysinternals tool called, what is it, TCP view. So again, this one runs in the command line. It's showing you real-time network information. You know, if I launch this, what IP address is it trying to ping out to? You know, we see things with the IPs and the ports and connections established per process here. So this can be very helpful to us, making sure it's, all right, it's not Google Chrome that's doing this, it's my evil application that's doing connecting to this IP address that it shouldn't be connecting to. So just to wrap up the whole presentation, I have a couple of malware analysis examples that I'd like to go through. So two different examples. The first one is an open source keylogger called Logkext. And the second example is a found in the wild Imuler piece of malware. And this one is a file and screenshot stealer. So Logkext, anybody can go ahead and download this. I believe it's on Google Code, possibly on GitHub now, who knows. So Logkext, you can download a package file. Double-click the package file, install it, probably on your spouse's computer, somebody you want to spy on, let's say. You press continue, go through all the regular setup instructions and things like that. And finally, by the end of it, it pops up this README document, this HTML document in Safari, basically showing you, hey, this is how you use it, this is how you get to the keylog file, so on and so forth. So a few examples using the tools that I was showing you before. So newproc.d. This is showing us, this is executing from the Logkext 2.3 package file that was located on Cliff Stoll's desktop. We see file, executable files that are associated with it. There's this Logkext keygen file. It looks like it's installing launch daemons, which is a persistence mechanism. So Logkext plist, we're going to want to go look on the drive later on and take a closer look at that one. We see this open command. It's opening up this Logkext README. That's when it's opening up that HTML page in Safari. Then right at the end, we're doing some kext loads and unloads. So it's installing a kernel extension. When we actually installed this application, it asked for user credentials, so it could install that kernel extension. So FS usage, a couple of examples there. We saw that, okay, Finder is getting attribute list for that Logkext package. We see syslog is writing files to the install log. Again, that kernel extension. So all of these MDS right here, all those MDS services, that's the metadata service, or that's Spotlight going in, basically indexing a lot of this information. And right at the end, we have Safari basically opening up that opening up that HTML page and showing it to us. Now, the second example, we have Imuler. So this one was basically given to, hopefully, victims that would double-click what looked to be like these JPEG pictures. So these last two are actually applications. We can see that a little bit over here if you see the application type here. So once these are double-clicked, a picture will come up to the user. All in the background, you're actually getting compromised, and there's all sorts of stuff going on. And by the time it's done, it actually has replaced that application with a JPEG picture. So if you look back, you can actually say, oh no, that was in fact a JPEG. I don't know what was going on with my system during that time. So what does this look like using FS usage? So FS usage with the -exec filter shows us that we have file agent, bin sh. Now this is where we get caught off. If you can see here, this is without the -w. So where it's all these file paths are getting cut off. But for the sake of a screenshot, you kind of have to do it. But just be aware of that. We have private temp launch ICS 000 sh rm. And what this is actually doing is it's storing like a script in private temp launch ICS. It's opening it, it's running it, it's removing files, it's adding files, all sorts of really great stuff. So taking a more GUI-based approach, got a couple of examples of fseventer. So to start off, we have our group photo. It's stored on this user's desktop under a JPEG picture. Say the user double-clicks this, a copy of it gets launched from /private/temp. A script is created, launch ICS. And all these other files are created. So we have two files here. We have scheduled sync under launch agents and scheduled sync.plist under launch agents. So this one, if we take a look at it on disk, this is actually a Mach-O executable. And this is the actual launch agent that is executing this scheduled sync executable. So that's the persistence points. That's the piece of malware that we would want to go take a look at a little closer. And we also have this comp back file that gets created, but I'll talk about that in 2 slides or so. So cleanup. We see that all these little red X's basically says, hey, this file was deleted or terminated. This group photo, this dsc0831.app, gets removed from that directory. Basically, it's getting replaced with that JPEG picture. We also see it cleaning up everything under that .app. That .app, again, was a bundle, so there's all these files that get removed and deleted from the system. And last up, we actually get beacons using TCP dump. So this was a legitimate bad website, ouchman.com, but once you executed this Imuler malware, it would automatically start beaconing out on a regular basis to ouchman.com. And we have TCP running in the background while we're doing our execution. We can easily see that it's trying to beacon out or phone home to this particular domain. So that is the end of my presentation. I do have a couple of resources and references here for you. If you are interested in actually playing a lot with the malware, I highly recommend going to specifically contagiodump.blogspot.com. She has a whole zip file full of Mac malware, and a lot of these samples came from it. So go ahead, download it, play with it. And if you need to email me, you got questions, you got comments, please feel free to contact me. I'm at IamEVLTwin on Twitter. Email address is oomp@csh.rit.edu. And I do have a website, macforensics.com. But I do hope to see you all in class one day doing some very awesome Mac forensics. Now it's time for the question and answer section, so I'm going to shoot this off to Trevor, and he can moderate that.
Thank you. Looks like we do have a couple questions. First, is reverse engineering part of forensic or vice versa?
I guess it really depends on what side of the house you're on. So I am a forensics nerd by default, I guess you could say. So in my experience, I would do the forensics first. I would find a piece of malware, and if it was simple enough, I could get a lot of information, a lot of triage information. You know, what files did it drop? Where would it connect to? You know, things like what registry keys it would, you know, write to and things like that. But maybe if it was a slightly more advanced piece of malware, it was packed or it was doing, you know, some crypto functionality or something like that, then I'd probably give it to one of the more full-on reverse engineers that was in my office at the time.
Great. Next question is, where is the best place to find sample Mac malware?
Well, I think we answered that one. So yeah, Contagio is really great. Open Malware, malware.com, VXShare, all really great websites to download some Mac malware. It is few and far between. That's why I like Contagio's site so much, because you just put it in a giant zip file that we can download and play around with.
Okay, and next question, what was the name of the book you recommended again?
The book was called Mac Internals, Mac and iOS Internals. So there is actually an older book called Mac Internals, but it's been updated, not by the same publisher or anything like that. And I think it came out in about 2012 or 2013, but it is available on Amazon's website. And that's by Jonathan Levin.
Great, thank you. That was our final question, so with that, I would like to say thank you so much to our featured speaker, Sarah, for bringing this content to the SANS community. To our audience, we greatly appreciate you listening in today. For a schedule of all upcoming and archived webcasts, visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.
Thank you.